Welcome again to part 18 of Alpha Found. This video is important to understanding the meaning of the perturbation risk model. Although for now I am maintaining the assumption that the covariance between perturbations is zero, the results of the simulation contain much insight. More important, the graphs of the results show us, or show me anyway, why alpha is so elusive. Here are the fixed parameters of the simulations. The only parameters that change from one set of conditions to the next are the perturbation risk parameters. To begin, from the last video, here are the conditions we are simulating. Here are the numerical results of the simulation. It may be difficult or time-consuming to read Table 18.1, but if you take the time, you will see how the various market statistics are just as predicted when the sample size is large. There really is not much worth talking about when comparing the expected values to the simulated values. The real beauty of the simulation is in the graphs. Figure 18.1. Expected alpha as a function of the perturbation risk ratio for constant expected excess return set to 10%, constant ideal betas, and zero average perturbation return. Figure 18.1 shows how expected alpha changes with the perturbation risk ratio while expected excess return does not change. Importantly, the changes in expected alpha are not linear with respect to the perturbation risk ratio. The rate of change for the expected alpha flattens as the ratio increases. The one point of intersection occurs when the expected alphas are zero, which is scenario 4, CAPM expectations. In some ways, Figure 18.1 is half the punchline of all the videos, since investment manager returns are evaluated on alpha. The blue curve is potential expected alpha for the high CAPM beta portfolio, while expected excess return is fixed at 10%. The red curve is potential expected alpha for the low CAPM beta portfolio, while expected excess market return is fixed at 10%. The different points on the curve are dependent on the perturbation risk ratio. For any point on the blue curve representing an expected alpha of the high CAPM beta portfolio, the corresponding red point on the same vertical line is the expected alpha for the low CAPM beta portfolio. The intersection point is what we would expect for CAPM, which is scenario 4. Alpha as measured by OLS is a point, but expected alpha is now seen to be a curve of potential values, each with the same realized arithmetic average return. That is why alpha is so elusive. Expected alpha is not a point. It's a curve of potential expected values. The expected point on the potential expected alpha curve is determined by the perturbation risk ratio. Since all the points on the expected alpha curve leave average return the same, it must mean the expected CAPM beta is also changing. That is, expected alpha and expected CAPM beta move in concert such that the average arithmetic return is unchanged. The next graph shows expected CAPM beta. Like expected alpha, expected CAPM beta is a curve of potential values. Figure 18.2. Expected CAPM beta as a function of the perturbation risk ratio for constant expected excess return set at 10%. Constant ideal betas, and zero average perturbation return. Just as with expected alpha in Figure 18.1, Figure 18.2 shows how expected CAPM beta changes with the perturbation risk ratio in a nonlinear fashion, while ideal beta does not change. For any given market return and underlying risk parameters, expected alpha is determined by market return multiplied by the difference between ideal beta and expected CAPM beta, while expected CAPM beta is determined by ideal beta and the perturbation risk ratio. If the curve of potential expected alpha is half the punchline, then the next figure is the remaining half of the punchline, since Sharpe ratios are the other major way investment managers are evaluated. Figure 18.3. Expected Sharpe ratio as a function of the perturbation risk ratio for constant expected excess returns set to 10%, constant ideal betas, and zero average perturbation return. Figure 18.3 shows that the relationship between expected Sharpe ratios is far from obvious, while ideal Sharpe ratios do not change. The intersection on the left corresponds to scenario 2, the middle intersection corresponds to scenario 6, and the intersection on the right is scenario 8. Anything to the right of scenario 8 corresponds to scenario 9. It is not clear from a visual inspection of Figure 18.3, but the expected Sharpe ratio of the market is at a maximum when the perturbation risk ratio equals 1, which is condition 1 in Table 17.1 and 18.1. The expected Sharpe ratio of the market reaches its minimum at the two endpoints, when the perturbation risk ratio is 0 on the far left, and also when the ratio is infinity on the far right. To summarize, although the ideal parameters and expected market return is constant in the simulation, the various expected values of the statistics traditionally used to evaluate portfolio performance vary significantly depending on the perturbation risk ratio. That is, identical average portfolio performance can be evaluated differently due to events that do not affect arithmetic average return. The consequences of the perturbation risk model are now on display. If all someone wanted to know is what it means, these graphs tell us what it means, mostly. However, the assumption that the covariance of the perturbations equals 0 is still in play. Much more must be discussed in order to get underneath what is going on. The next step is to make an effort to work the problem backward to see how different interpretations of the same data are possible. Working backward is more difficult, and the effort will ultimately be frustrated. As a result, we will be forced to let the covariance between the perturbations not equal 0. There is still much more to come.